Welcome to the continuation of our study of material balances. I'm Dr. Christy Patton-Lukes, and we're looking at problem-solving technique today. So just as a quick reminder, we've looked at balances. We have the input plus generation minus output minus consumption equals accumulation as our general case, and we have several special cases, in particular steady state, where input plus generation equals output plus consumption. Now, we're going to be initially looking at the case with no reaction, so the generation and consumption terms will be disappearing in our expressions. Now, we also could be looking at batch systems, in which case we've got a system with no flow, and the amount of material in at the beginning and the amount at the end, the difference between those is the accumulation. So the input plus generation equals final output plus consumption. But again, if we're dealing initially with no reactions, then those terms go away, and we'll say that the initial input equals the final output if there's no reaction. So we want to have a system for doing material balance calculations. We're going to start with a very methodical approach. We're going to first choose a basis for calculations. Now, you'll slowly learn better what this really means, but we always want to have a size for our system, which means that the size may be given to us in the problem statement, in which case use that. Okay, maybe you have a feed flow rate of 5 kilomoles per hour. That could be your basis. But if there isn't one given, or if the one you have given seems challenging to use, you can just choose anything. Typically, I use numbers such as 100 kilograms of feed. The next step we're going to do is to draw a PFD, that's those process flow diagrams. Always try to draw them from left to right. Label your streams, draw your system, your process as a box, and the material going in at the beginning of time or into the process on the left, the product coming out on the right. Next, we'll be building a couple of tables. These steps are sometimes going to make it seem like we're doing extra work, but if you start doing these on the easy problems, it will make the later problems so much easier. So the first table we'll build is a material balance table. This is just going to be a summary of all of the information given in the problem statement about how much and what components are flowing in each stream. Next, we're going to do a degrees of freedom table. This is where we're going to make a decision about whether or not we have all the information we need to be able to solve the problems. And it will, as the problems get more complex, it will guide us as we make our decisions about what step to do in which order. Once we do this, we'll be able to write a system of equations and solve them. There will always be extra equations. We'll use those to verify the answer. And then, this is a frequently forgotten step, don't forget to answer the question. So let's look at an example. I'm going to look at moist air, which just simply means it's a mixture of dry air with water vapor. It's going to enter a dehumidifier at the rate of 23.2 kilograms per minute. Liquid water drains out of the dehumidifier at the rate of 0.5 kilograms per minute. We want to determine the mass flow rate of the dried air that leaves the dehumidifier. Now, this is a very simple problem. So we want to take this, though, step by step. So it says that step one is to choose a basis. So in this case, they've given us a couple of flow rates. It is usually much easier if you work with the feed. 23.2 kilograms per minute in the feed is a very convenient basis. Now, recognize that this is totally arbitrary. I could have chosen the 0.5 kilograms per minute of water out. I also could have done something crazy like 100 kilograms being fed in. If a flow rate is given, that is probably your best choice. Now the next step says draw PFD. So a PFD basically is a box. In this case, the box is the dehumidifier. Okay. We are going to draw our feed coming in on this side. And the feed, stream F, I'll call for feed, is 23.2 kilograms per minute. And it contains water and dry air. Now, I don't know exactly how much of each it contains. We're next going to have the product that leaves. Now, I know I have one stream that is the liquid water. I'll just call that W for liquid water. And that flows at the rate of 0.5 kilograms per minute. And it contains H2O only. Okay. And then I also am going to have the rest of the air, right? This is not complete at this stage because the air is not leaving the system. And I know that the air has to go someplace. So I have this other stream that I will just simply, I'll call it A for air. And it's going to contain H2O and it will contain air. I don't know how much H2O, I don't know how much air. It will be all of the air. So, the next step is to do a material balance table. Now, a material balance table for a problem such as this is truly going to be overkill. Okay, so on our material balance table, what I recommend is you first of all come up with columns that are going to be each of the streams. So I have the feed, I have the dried air, and I have the water. Then on my columns, they are going to be based on my components. So I have the dry air and I have the water. And then I always have a total. So this is going to be the basic setup for my tables. I list the streams across the top, and then I list my components and then add them up for a total on the side. Now, the information I have, I want to write into the table here. So this is 23.2. I'm going to make sure that all of these are in kilograms per minute. I'll write that down over here. 0.5 kilograms per minute. Oh, wait. I put that in the wrong spot. Not a problem. 0.5 kilograms per minute here. And I'm trying to solve for this. Now, up here would be where I would list about the components. I could choose to do these all sorts of different ways. It's not really necessary for this problem, but let me just do these in kilograms of air per kilogram total. I'm using mass flow rate, so I'll use mass fractions, and kilograms of water per kilogram of dry air. Now I know that the water stream is 100% water and no air. I know that this stream is got a mixture of the two and that they have to add up to 1, so I'll call it X and 1 minus X. And this one is going to be, well, something different, Y and 1 minus Y. Now, this information here is unnecessary for the problem statement we have. However, I'm just trying to get you accustomed to some things we'll be seeing in the future. For our problem, we really only needed the totals. So for the next, we're going to do a degree of freedom table. The degree of freedom table is going to be a way for us to analyze how many variables I have and so forth. So in this particular case, we'll flesh this out a little bit better in some future lessons, but here my top is going to be for my dehumidifier. I do these process by process. Material table, I look at streams. Degrees of freedom, I look at processes. So I'm going to list my variables. Okay? Now the way I've set this up, I have the variable a that I'm really looking for, and then I also have x and y, but I'm not interested in those. Okay, so I have the variable list, so that means the number of variables is going to be 1 or 3 if I include those, but I'm only solving for the 1. So now I need to come up with my equations that are possible. So I can write material balance equations. So the number of material balance equations that I am going to be able to write is I get to do 1 per component. Okay, so I have water and air, so I can write 2. Okay, now I could also write a total material balance, which is what I'll be using in this case, but that's going to be redundant. It's extra information. And so I would have that. Then I'm going to have things like, sometimes I have a sum of x equals 1 equation. In this case, I've already written those out, so I don't have any of those to solve for me. And then I figure out my degrees of freedom. I'm going to take the number of variables minus the number of material balances minus the sum of x's. In this case, for the total system, I get 3 minus 2 equals 1. That means I have 1 degree of freedom left. This problem is not well specified. I cannot solve for all 3 variables. Okay? But how about if I'm only looking for this 1? Well, if I'm only looking for this 1, then I only need to write the total. So I have my 1 material balance. I still don't have any of these. And in that case, I have 1 variable minus that 1 total material balance, and this is 0. You're ready to solve the equation. As soon as you have degrees of freedom equal to 0. Until then, you still need to be digging for more information. All right, so now we're going to write our system of equations and solve them. In this case, I'm only looking for A. And so my equation is input equals output. I have the stream 23.2 kilograms per minute, and out I have A plus W, which is 0.5 kilograms per minute. And so A is going to be 27.7 about 22.7 kilograms per minute. Okay. Now this may seem like overkill, right? It is for the little simple problem. You could have done this one in your head without anything else. So verify your answer. Make sure that it all makes sense. Okay, so 22.7 plus 0.5 is 23.2. Yeah, I'm happy with that. And then answer the question. In this case, that's not much different than just solving the equation. But remember, it says find the dried flow rate, or the dried air flow rate, okay, that leaves the dehumidifier. So I want to answer it. Be sure to include units. So this concludes this lesson. In the next lesson, we're going to continue looking at some examples that will be increasingly more challenging than this one.